All right, good afternoon, class. Welcome to part two of Ferrous alloy systems. Now we'll be getting into the general microstructures, but first I need to provide some background on the type of ferrous alloy systems we will be discussing. First of all, what are ferrous alloy systems? We're going to be going over elements and designations for the following: plain carbon steels, high strength low alloy steels, tool steels, stainless, and cast iron. We're going to be discussing single phase structures and two phase structures. So plain carbon steels, what are they? They're typically steels that have anywhere from 0.008 weight percent carbon upwards to 2%, 2 weight percent carbon. So the low carbon steels are steels that have anywhere up to about, and this varies, but it's approximately 0.3 to 0.35 weight percent, depending on what your resource is. Medium carbon steels take off after that. They go from the 0.35 up to about 0.7, 0.75. And then you have your high carbon steels that are above 0.70, which cap out at around 2.0 weight percent. So what are the differences? I mean, carbon is really the most important alloying element when you're talking about ferrous systems. But to separate now between plain carbon steels and the other family of steels is you're looking at plain carbon steels do not have alloying elements added. Typically, manganese, silicon, copper, sulfur, and phosphorus, and those are at even limited levels. So really, it has nothing that has been purposely added to the material to change its nature. Alloy steels, on the other hand, do have alloying elements that have been added for specific properties. And here we go, first ASTM standard A289, A29, sorry, is your standard specification for steel bars, carbon and alloy that are hot wrought and are the general requirements. So when we're talking alloy content that's purposely added to steels, you're taking a plain carbon steel and now you're adding chromium, you're adding manganese, molybdenum, nickel, and it's based on what you want to achieve as your end result. What do you want your material to perform like in the end? So, adding chromium, you got a couple pointers here on why chromium is good to add to your material. Increases hardenability, increases high temperature strength. Manganese also increases hardenability, prevents hot shortness, and increases banding. Molybdenum, once again, increases hardenability, toughness, strength at elevated temperatures, and decreases temper brittleness. And nickel increases the strength within ferrite and increases hardenability as well. So the new terms that I want you to define in the weekly summary is the term hardenability and banding. So there were aspects of the designations that I use that might throw people off, but essentially these designations kind of help you gauge, okay, well, what material am I dealing with? You have your vanilla grade plain carbon steels. Those are your 1000 series steels. Then you have your chromoly. It's your 4100 series. Then you have a chromoly nickel steel, which is a 4300 series high strength low alloy steel. The nickel content in a 4300 series is high. So in high, we're talking 1.8%. Okay. You compare that to kind of almost like a downgraded version of a 4300 series, you have an 8600 series, which is also a nickel chromoly steel, but the nickel content drops. It's almost a third of what it's found in a 4300 series, but the manganese contents are higher. Those X's at the end of the designation is basically the weight percent of carbon, and it's illustrated as 0.1%. I was trying to find the words there. So, for an example, if I say 1018 low carbon steel, it doesn't mean that that particular steel has 18 weight percent carbon. It's 1/10 of that. So you put a decimal in front of that number, and it's 0.18 weight percent carbon. 4140, same thing. You need 0.40 weight percent carbon. 5160, very commonly used in bladesmithing, is a 0.6 weight percent carbon. And then an 8620, and that is a 0.20 weight percent carbon. Those last three that are listed are high strength low alloy steels. Tool steels, their purpose is for cutting and forming, and they require a higher hardness, higher strength, higher toughness. So the alloy content within these materials are elements like tungsten, molybdenum, vanadium, chromium, manganese, and of course, carbon. Typically, the heat treatment for these materials involves quench and temper for them to be useful, high carbon martensite, and the formation of primary carbides is what helps provide hardness for these materials. Primary carbides, they can only be mechanically broken up. Heat treatment, you will not get those to dissolve back into the matrix. An ASTM standard for tool steels would be ASTM A681. Stainless steel are low carbon steels that contain about a minimum 11 weight percent chromium. And it's that chromium layer that forms on that surface that gives it the stainless term. These are typically identified by structure. Types of stainless steel, you have the ferritic, which is chrome only, austenitic, which is weldable, martensitic, which is also chrome only, is also that is heat treatable. Duplex stainless steels is a balance between austenite and ferrite of equal proportions. Precipitation hardened are heat treated by solutionizing, and then a second process called aging. And typically for these, aluminum, molybdenum, chromium are added to form the precipitates, which are its strengthening mechanism. So for stainless steels, a common ASTM standard that's used for stainless steel bars and shapes is A276. One for precipitation hardened stainless steels is A693. Then we have our cast irons. These are produced by pouring molten metal into a mold and just allowing it to solidify. There's no additional process after that. Once it solidifies, you pop it out of the molds and off they go. They can either be machined or they're cast as is. Typically, cast irons have high silicon and carbon content. Chemistries can be problematic because it's a casting. The way it solidifies, you can end up with a lot of different areas of chemical segregation. It's not as controlled as it is in a wrought product. But most cast irons contain carbon in the graphite form. And the graphite morphology is what has a strong influence on the mechanical properties for cast iron. So method for measuring and evaluating those structures of graphite in iron castings is ASTM A247. Types of cast irons include gray cast iron, ductile cast iron, white, mottled, and malleable cast irons. Each of those, I've listed a common ASTM standard for evaluating and looking at either mechanical properties and or chemistry. One thing to note is white cast iron does not form graphite. Instead, the carbon is in cementite form. And then the mottled is just a mixture between gray and white cast iron. So what does all this mean, and why did I go through all of that? Well, in order to understand a microstructure, you have to know what your material is and what to expect when you look under the microscope. So you have to know what single phase structures are found in these ferrous alloy systems. And so here I have listed 7 different types of single phase structures that form in the families of or classifications of materials that I just briefly went over. But you have alpha ferrite, austenite, delta ferrite, cementite, primary carbides, graphite, and then martensite. So looking at alpha ferrite, it's alpha iron, so it's body-centered cubic crystal structure. It has an 0.008 weight percent carbon maximum. Grain structure is described as rounded grains that do not have twinning. You can see that this is an equiaxed and uniform distribution of grains throughout this entire image. And the typical hardness is on the low range. It's 100 to 250 Brinell. When you compare that to austenite, on the other hand, this is gamma iron, so it's face-centered cubic. It has about a 2.1 weight percent carbon maximum that can be dissolved within, but it's not stable at room temperature. It's not magnetic, so if you ever hear somebody say, oh, this is an austenitic stainless steel, it is not magnetic. And grain structure in this case, when you compare this with the ferrite grains, the grain boundaries look more angular, so it gives you that angular edge, and the telltale sign are the twin boundaries located within the grains. Those twin boundaries are these guys right here. That would be a twin. You got more twins here, more twins up here. Okay, so those are twins that are within that grain boundary, within that grain. Hardness, this is also soft, ranges between 100 to 400 Brinell. Then you have delta ferrite. Delta ferrite is only stable in stainless steel. This has the smallest amount of carbon, so it's going to be found in stainless steels, which are already low carbon as is. Delta ferrite is also a body-centered cubic structure, and that's why iron is allotropic. It has the ability to change crystal structures depending on temperature. But the delta iron in this case are these little guys that are dark and linear. And the only way you can observe them is in the etched condition. And when they're etched, they're only outlined. Okay, so they really don't have grain boundaries. These are more like interfaces between this and the grain structure. Okay, so those are examples of delta ferrite. The dark etched, I guess these dark features here are inclusions of some type. It's kind of hard to say at this magnification, but the grain structure is austenite. Okay, you could tell because here's a grain with twins. Here's another grain with twins. Another grain with twin boundaries. So those are, this is essentially delta ferrite in an austenite matrix. Then we move on to cementite. Cementite is on the far end of the phase diagram when you're looking at the iron-iron carbide phase diagram. So the weight percent of carbon is 6.67. That's a lot of carbon. And it's very hard, it's very brittle, and it does not etch with nitol. Matter of fact, it actually has a slightly pink hue to it when you're comparing it to ferrite. So that's how you'll be able to tell the difference if you etch with nitol, because as we know, ferrite really doesn't etch well with nitol either in developing grain boundaries, right? So you have a white phase, any cementite would show up kind of pink in color. If you use pickerel, it will outline it very nicely. So you'll be able to tell the where the cementite really is. So it really does not have grain boundaries. When you're looking at cementite, you will not have a grain of pure cementite. So the cementite in this case are these regions here. These are the light regions. They don't look pink in this image here, but this is all cementite. Okay. Everything else in this image, I'll let you guys guess, but it should be perlite. These are all perlite grains. Okay. Looking at primary carbides, like I said, these do not dissolve during heat treatment. They are harder than cementite, and they're typically present in tool steels because of the fact that they are, when you're looking at primary carbides, you're looking for strong carbide forming elements. And strong carbide formers are elements like tungsten, vanadium, molybdenum, titanium, chromium, niobium. Those all form very strong carbides. The stoichiometry in which these carbides can be present are M is the metal. So a tungsten carbide would be an MC stoichiometric carbide. M2C, M6C, these are like moly carbides. Titanium carbide is also like an MC. The most famous one is the M23C6, and that one is the chromium carbide. And those typically form in grain boundaries, which is a big no-no in high temperature use, or actually also in high temperature use in superalloys and or stainless steels. Looking at graphite, I know I had a slide talking about the differences between flake and nodule. This is the most stable form of carbon that you're going to find. The primary graphite is formed during the cooling process, and then the secondary graphite can form during heat treatment. So all because you have a cast product doesn't mean that's typically the finished condition. It can go through normalizing. It can also go through quench and temper as well. So that's where secondary forms of graphite will form. ASTM A247, as I mentioned in a previous slide, is the way you would analyze the flake graphite in castings. So martensite, speaking of quenching, this forms with rapid cooling. You will not find martensite as a phase on the phase diagram. This is something that you would identify in an IT diagram, which I'll explain later when we talk about heat treatment. But this is a body-centered tetragonal crystal structure, and it has a needle-like appearance. As you can see, this is very different from ferrite, austenite, perlite, and the hardness for martensite typically depends on the amount of carbon you have in your material. Hence the reason why I went over the different designations for carbon. How can you tell if you have a high carbon versus low carbon steel? That's going to vary on your maximum hardnesses that you can obtain or achieve in these parts by quenching. So if you take a 1010 carbon steel and you quench it, then typically your highest or maximum hardness you're going to get out of that is about a 38 Rockwell C. If you take a 1065, which is 6 times more carbon, you're able to almost double the hardness. So after single phase, you have your two-phase structures. So you have perlite, spherodite, and bainite. When it comes to perlite, I've already discussed this a couple times, but it's your lamellar eutectoid of ferrite and cementite. Ferrite in this case is going to be your light regions. Cementite is dark. This particular phase takes time to form. So if you cool it slowly, then the interlamellar spacing will widen. And you're looking at hardnesses, maximum hardnesses at like 85 Rockwell B. If you tend to cool it slightly quicker, not quench it, you don't quench it in water, but instead pull it out of the furnace and let it air cool in an air-conditioned room or something like that, or force air, then you'll end up with a fine interlamellar spacing. So kind of the way I can get you guys to wrap your minds around this is, think of a double stuffed Oreo as your wide interlamellar spacing. Why? Because the cream on the inside of the Oreo would be your ferrite, right? Nice and soft. And then your cookie on the outside is dark. That would represent your cementite. So if you were to take an end off of each Oreo and then stack them, you would have the cementite, ferrite, ferrite. Since it's double stuffed, the spacing between the cementite is going to be further apart. So my analogy for using that for fine interlamellar spacing is, how about Oreo thins? That would be the best way to describe a fine interlamellar spacing, is to do the same thing, compare the two of them, and you're going to see that the interlamellar spacing is different for each. This will have a range of hardnesses when you're looking at the Brinell scale, anywhere between 175 to 400 Brinell. And that can change. Once again, it's because of the rate of cooling, you get a range in which your hardness will be. So if we were to take a material like a tool steel, something that has a lot of carbon, this particular material that we're looking at on the screen right now is essentially a eutectoid steel, which means it's got about 0.77 weight percent carbon. So if we were to take something like that and then spherodize it, what ends up happening is you create spheridites. And this is a phase that contains ferrite and cementite. So all of the lamellae that were in the perlite, the carbon has gone from that dark lamellar structure now into spherical particles of cementite. And this is an equilibrium structure. So the heat treatment made the carbon take a new form. And these larger grains that you see here, these are ferrite grains. This guy, these are ferrite grains. That's a ferrite grain with a little bit of cementite on the surface. Here's another ferrite grain. But really, all of the white that you see, I'm going to use the red. So these little tiny particles here, that's your cementite. All of the white in between is your ferrite. So all of this right here would be your ferrite. Okay, so you have some proutec, you can have some proutectoid ferrite grains, and then you have your mixture of cementite and ferrite as your microstructure. This is really nice to do to tool steels better than trying to section cut anything that has been quenched and tempered. This would make this very workable for the process, for any forming process. Then we get into bainite, and then you have, just like you have a coarse and fine perlite, you have a upper and lower bainite. The difference is that this also, well, once cooled, this will be a final product. There would be no additional heat treatments necessary to form bainite. But this is composed also of ferrite and cementite, and it has a feathery type of appearance. It does etch darker than martensite, and that's why it's a little easier to distinguish the difference between bainite and martensite. When you're looking at these two micrographs, your bainite are all the dark regions, and the light regions are martensite. Okay? And the martensite happens to be in the as quenched condition. So there's martensite. This over here on the lower image is martensite. All the dark features represent lower bainite for that lower image. So if you're trying to kind of gauge a, looking at how, well, you know, perlite is also ferrite and cementite. Bainite is ferrite and cementite. So upper bainite, since it's this kind of looks more like a, if you were to look at this grain right here, that looks like that could also be perlite, right? So that's why upper bainite has a resemblance of perlite. And then when you're looking at the lower bainite, just like martensite, it has a needle-like appearance, very sharp appearance to it. So the properties of bainite are something in between perlite and martensite. Perlite, you typically have higher ductility, lower strength, lower hardness. Martensite, complete opposite. You have high strength, high hardness, low ductility. So if you want something in the middle, then this would be the phase that you would want to obtain in your structures. So that is the gist of alloy systems, general microstructures. We haven't gotten into different heat treatments or anything like that yet. But between this week and next week, we're going to be covering more microstructures, more images, and I'll be providing you guys with samples to start going into the lab and finding this stuff out for yourself. So for this week's assignment, it's to complete the assignment on the Ferrous alloy systems, and then move on to complete the 2 quizzes that I have set up. And that will be it.